This is Chapter 7. We're talking about partial derivatives. So first we talk about functions with multiple variables. So we can have a function that has two or more variables in it, and if we were to try and graph a function that has, say, two variables, then we're going to get a 3D surface. So in this first example, you can see that our equation is a z equals, and we have a function of x and a y in there. So that is a function of two variables, and it creates some 3D surface. And in example 2, I have a new formula with two variables. So it's a function of x and y. And we get this nice saddle looking surface. Now one of the things that we're going to do in section 7.1 is we're going to evaluate our function at a point. So we want to find f of 3, 5. So f of 3, 5, the 3 is x, the 5 is the y. So we're just going to plug x and y in. So plug in x equals 3, and y equals 5 into our equation. This shouldn't be anything difficult. We've done this in many math classes. So 3 squared minus 5 squared equals 9 minus 25, or negative 16. Now you will want to make sure you look at the Cobb-Douglas function in our textbook. That is an application. You will be seeing it on your homework. But again, that's not new. What is new is now how do we start applying slope to that, or derivatives. So if I was to look at this function, okay, so we have a function with e to the negative x squared plus e to the negative 4y squared, so it's a function of x and y. And let's say we pick a point, maybe this point, and we want to know what's the slope. Well, if I go up in this direction, it would be one thing. This direction would give me a different slope. This direction would give me a different slope. This direction would give me a slope. Any direction I go in, it's going to give me a different slope. And so how do we define what slope are we talking about? So we had to go through and we had to narrow it down. So now what we're going to do is we're going to pick a point and go in just one direction. So what we might want to do is go in the x direction, so go straight out in the x direction, and that would give you one slope, and that would be the partial of f with respect to x. So we do a partial derivative with this little funky d, and because we check the slope going straight in the x direction, we would say it's the derivative with respect to x, or this is kind of the slope with respect to x. So if you go straight in the x direction, that would tell you what the slope is with respect to x. Notice that y stayed the same. We didn't change the y, we just checked the x. Now let's pick a different point up here. Let's say I wanted to see what its slope is with respect to y, or how it changes with respect to y. So I'd go straight out in the y direction. That would be the partial of f with respect to y. So because there were all these infinite possibilities of how to find the slope, we had to narrow it down. So we look at the slope in just the x direction or the slope in just the y direction. And those are our partial derivatives. So partial of f with respect to x means if we were to change x, how much does z change? And again, we're assuming we keep y constant, or y doesn't change. Okay. Or the derivative of f with respect to y, okay, tells us, okay, keep x the same and only change with respect to y, so we'd be coming out again in this y direction. So that's the theory. Now how do we do that? So if we wanted to find, say, the partial derivative of f of x with respect to x, so this is telling us find partial of f with respect to x. To do that, we'll take the derivative as normal, but we only worry about the x variable. We're going to treat y as a constant. Now, this isn't actually new, it's just a new notation, and okay, we're making it more official. We've done it before. We did it way back in section 1.7. Okay, so it's not actually new. When you do this, if you're doing the partial with respect to x, only worry about x and just treat y as a constant. So let's try example 4. Here's my function x squared minus 3xy squared plus 7y, and we want to find the partial of f with respect to x of x squared minus 3xy squared plus 7y. Okay, so as we do this, we only care about x, we treat y as a constant. So the derivative of x squared, that would be 2x minus, okay, now the derivative of 3xy squared. 3 is a constant, so let's leave it there, 3 times. The derivative of x is 1. Okay, now times y squared. In this situation, y is a constant, so we just leave it there. Okay, remember when you're taking the derivative, if you have a coefficient or a constant that's timesing your variable, you just leave it there still as multiplication. Plus, now the derivative of 7y. Now y is a constant, so that means it could be just like the number plus 7, and the derivative of that would be 0. So we get 2x minus 3y squared. And that's it. We just did a partial derivative, not that bad. Now let's do the partial derivative with respect to y. Again, of x squared minus 3xy squared plus 7y. So we go through term by term. First is x squared. The derivative of x squared, well, x is just a constant. The derivative of any constant by itself is 0. Okay, minus, this is a 3 times our variable, so we leave it there. Now x is just the constant as well, so we'll leave it there. Now the derivative of y squared would be 2y. Plus, the derivative of 7y would be 7. So this is going to give us 7 minus 6xy. So for example 5, continuing on, let's evaluate the partial of f with respect to y at x, y equals 4 sun. So let's just remind ourselves the partial of f with respect to y equals 7 minus 6xy. Okay, so what we want to do now is just plug in our points x and y. One of the ways we can write this is if we're plugging it in, we'll write it like this. Okay, so this tells me I'm evaluating it at those points. So it's going to be 7 minus 6 times 4 times 7. Negative 161. And let's look now at example 6. So we have our function is x squared minus y squared, and we want to find both of our partial derivatives. So let's do it with respect to x first. So I just go through each term. Derivative of x squared would be 2x minus, now the derivative of y squared, that's just a constant to us. We don't care about y. So it's just going to be 0. So my answer is 2x. And the partial of f with respect to y is going to be, okay, so derivative of x squared, that's a constant, we don't care about that, so that's 0, minus derivative of y squared is 2y. So we get negative 2y. And those are our derivatives. Now, just like before when we took derivatives, we then did second derivatives, so we can do second partial derivatives. The notation on this looks a little bit nasty. You have to sometimes think about it or look back in the book again. So this derivative, so it's the little partial symbol with the 2f and partial x2. There is a reason that the 2 goes onto the partial symbol, but the 2 goes onto the x. But it is technical, you probably don't care about that. Okay. So this is the partial with respect to x twice. So it means we're going to take the derivative with respect to x twice. This one, okay, when we do the partial of x, partial of y, you actually always work inside out on these ones. So we're actually going to take the derivative with respect to y first, and then we'll take the derivative again with respect to x. Okay, similarly, this next one, we work inside out, so we'll take the derivative with respect to x first, and then with y. Okay. And finally, if we have the y2, okay, that just means take the derivative with respect to y twice. Now, for simple functions, which means almost everything we do in this class, it turns out that our mixed partial derivatives, so the partial of x with respect to y, or, sorry, I just said that wrong. If we do the partial with y and then the partial of x, that will give us the same result as if we do the partial of x and then the partial of y. Okay, so it doesn't actually matter which order you do that mixed second partial derivative in. So for this example, we're going to go through and find all the second partial derivatives. So to start, let's write down what my first derivatives were. Let me scroll back up so I don't have to do it again in my head. So these are just our first partial derivatives we found when we did the previous example in this video. Okay, so these are our first derivatives. Now let's find our second derivatives. So first, let's find the second derivative with respect to x, or let's do the partial with respect to x and then do the partial with respect to x again. Okay. So that means we're going to come to the partial with x that we already did, and now we're going to take the derivative again, but we only care about x, treat y as a constant. So the derivative of that with respect to x is going to be a 2 minus 0, because we don't care about the y at all, or just 2. Now the partial, let's do the one with y twice. Okay. So we'll go to where we already did y once and just do the derivative with respect to y again. So the 7, that's just a constant, that's going to go away. This is going to be 6 times x is a constant, so leave it there, times the derivative of y is just 1, so negative 6x. Now let's do a mixed partial, so let's do this one. Okay. Notice we go from inside out, so we're going to start with the derivative of x, which means this one here. Okay. Now we'll do it with the derivative with respect to y. So now y is our variable, we ignore x. So 2x, the derivative of that would be 0, minus, now 3y squared, that would be 6y. So in this case, negative 6y. And one more color, let's do the mixed partial, where we go inside out, so we're going to do the derivative of y first, so let's do this one. And now take the derivative with respect to x, so x is the only thing we care about, so 7, that's going to be 0, minus 6 times the derivative of x is 1, and y was a constant, so we keep it here, so negative 6y. Notice that whether we did the derivative with x and then y, or y and then x, we got the same result of negative 6y.